Welcome back. In the last couple of videos, we've discussed type 1 and type 2 error, and in the last video, we also introduced the concept of the power of a hypothesis test. And so I thought we'd start today by reviewing what all those things mean. I've got a little bit of something to talk about before I get to what I teased in the last couple videos, which is a diagram that puts all of these concepts together in a way that's, I think, easier to see. So, let's review what each of these terms means. Type 1 error is when we make a mistake, right? It's an error. And type 1, if you remember, that's when the null hypothesis is true, because that's what we assume when we do a hypothesis test. When the null hypothesis is true, it would be a mistake to reject that null hypothesis. Once you know what type 1 error, it's pretty easy to determine type 2 error. It's the exact opposite. It's the mistake you make by failing to reject the null hypothesis when it's actually false. So it's the exact opposite of type 1 error. The power of a test? Remember, when we conduct a hypothesis test, what we're trying to do is prove that the alternative is true. Now, whether it is or not, we'll never know. But power is the ability to correctly reject a false null hypothesis, which is what we're trying to do. And we've also discussed some of the relationships between these quantities. Type 1 and type 2 error are usually fighting against each other. If you want to lower one type of error, that generally means you have to increase the other type. Type 2 error and power are directly fighting against each other. The larger one is, the smaller the other is. That's a definite relationship. And we said that type 1 and type 2 error could be reduced simultaneously, which would be ideal. We don't want to be making those mistakes. Only if we increase the sample size for our test. So, we've got a little bit of understanding of these concepts, and we'll get back to them in a little bit. But before we do, I'd like to discuss how likely it is that these errors are made can depend on several things. Sample size being one of them, like we said. The larger the sample size, the smaller your errors are going to be, and that also will increase your power. But there's also the idea of how accurate are your hypotheses. So, say in the potatoes example, our hypotheses were these. The null was that the proportion of potatoes that had blemishes was 8%, and the alternative, what we were trying to show, is that the potatoes, at least 8% of the potatoes had blemishes, more than 8%. So this is the hypothesized value. This is the one that will determine whether or not the potatoes get sent back or not. But what if the true proportion of potatoes that have blemishes on them was like 20%? 20% is a lot higher than 8%. Chances are, if the true proportion of potatoes with blemishes was really 20%, most of the samples of potatoes that we would get, we would see sample proportions a lot higher than 8%. It would make it much easier to correctly reject the null hypothesis. Because chances are, with a really high sample proportion, our test statistic is going to be very high, our p-value is going to be very small. We're going to reject a lot more. So, if the true difference between p, the population parameter that we don't really know, if the distance between that parameter and the value from the hypothesis are really far apart, that is going to increase our power. It's going to decrease the probability of type 2 error. Now, the probability of type 1 error, remember, you set that at the beginning of the test. But we're saying that the difference between p and this value, which we call P naught, can make a big difference in how large or small these things are. The difference between those two things, P and P naught, is called the effect size. So here's the summary of that discussion. The distance between the population parameter, which in our case, since we're dealing with one sample z-test, is P, and the hypothesized value, P naught, which is the number that we put in the null hypothesis, that distance is the effect size. And the larger that distance is, the larger the effect size, the higher the test power will be. And that will, in turn, lower beta, the probability of type 2 error. So type 1 error, remember, is alpha, type 2 error is beta, and power is just power. Okay? So the larger the effect size, the further away the true parameter is from the value you're hypothesizing, the easier it's going to be to reject your null hypothesis when you should, raising power, and raising power reduces type 2 error. Okay, we finally put enough of the pieces together here that we're finally ready for the diagram that I've been teasing for a while. That's going to put a lot of these things we know into the same place. So, let's suppose, for the purposes of this lecture, that we are testing these hypotheses. Our null is what it always is. P is equal to some value. And I'm not even going to specify what that value is, so I'm just going to keep it as P naught. This works no matter what that value is. And our alternative in this example is that P is greater than some value. So this is a one-sided test, greater than. This idea that we're going to be talking about, you could do it if this were a less than or a not equal to. It would look a little different, but the relationships would all be the same. And I'll try and remember to repeat that when we're done. Okay? But this is just for illustrative purposes. We have to choose a particular alternative. I chose greater than. Okay? So, here we have a normal curve. This is the sampling distribution of our sample proportion. And this curve, this green curve, represents the null hypothesis being true. So if the null hypothesis is true, remember that's this, that means that P is equal to whatever this value is. Okay? We would never know that when we're doing a hypothesis test. This is just theoretical. Okay? So if P is equal to P naught, then P naught is right in the middle here. That's our hypothesized value, and that is P. Now, this curve represents all the different samples you could get. What are all the different P hats you could get from a sample if this is the true population proportion? Sometimes you'll get sample proportions down here. Sometimes you'll get sample proportions up here. Okay? Now, we would reject this null hypothesis if the sample proportion we end up with from our sample is greater than, in this example, this value here. Okay? So what we're saying is we are going to reject the null hypothesis if our sample proportion is greater than this value. And I'm going to call this P star. And this P star value is dependent upon the critical value, which would be Z star. Okay, so let's write down some of this already. Okay, so we're going to reject the null hypothesis if P hat is over here, and that means we would fail to reject if P hat were over here anywhere. So I'm going to go ahead and write that in these areas. This is failing to reject the null hypothesis over here. All of the area over here. And then all of the area over here is going to be rejecting the null. All right. So, if the null hypothesis is true, which it is here, the correct decision is to fail to reject, which is all the area on this side. All of this area represents P hats where we will end up making the right choice. That means the area over here, where we reject the null hypothesis, That means we're making a mistake. That is an error. Which type of error is it when the null is true, but we reject it anyway? That's type 1 error. So we will label it as such. Let me use this here. We'll use blue. So I'm going to shade all of the area and label that as type 1 error. And that's alpha. Okay. So we are putting a picture to these concepts. If the null hypothesis is true and we reject it anyway, that's type 1 error. Everything we've talked about so far has been dealing with this green curve, which represents where the null hypothesis is true. If the null is true, which is that top curve, that green curve, and we reject, which means we're on the right side of this dotted line, then that's type 1 error, the blue area. Okay. Now, let's talk about when the null hypothesis is false, because we want to start incorporating type 2 error and power. If this green curve is where the null is true, then we should make a curve where the null is false. And for this particular hypothesis, p greater than p naught, this is where p naught is. So p, the true population proportion, has to be somewhere greater than it. I'm putting it in the middle of this curve over here. So we can see here, for sure, this is where the null hypothesis is false because our hypothesized value is way down here. And p, the true proportion in the population, is up there. Now, what can we say about this? Well, we know that we are going to fail to reject the null hypothesis if our sample proportion is on this side of the dotted line. If p hat is less than p star. So with this purple curve, we're establishing where the null is false. Alternatively, the alternative is true. Okay? So p is greater than p naught, and we are going to fail to reject if we come up with a sample proportion for our test that is less than p star, which is related to the critical value. So if the null hypothesis is false, which it is for this curve, but we fail to reject the null hypothesis because we're down here with our sample proportion, that's a mistake, right? If the null is false, we should be wanting to reject, but this is an error. This is the probability of type 2 error. So we already knew type 2 error is when we fail to reject the null hypothesis when it's false. The purple curve is the null hypothesis being false, and being left of this p star value is where we fail to reject, so that is where type 2 error is. And at this point, you can see that as long as these curves are where they are, and they are the shape that they are, if you increase one, you're going to have to decrease the other. And the other way around. So say for a given test, alpha is 0.05. Your probability of type 2 error is whatever this is. But if you want to run the test with a lower alpha, we have established that means you have to move this p star value to the right. But if this curve stays where it is and you move p star to the right, what happens to type 2 error? This area is going to increase as this dotted line moves right. On the flip side, if you're okay with a type 1 error that's a little bigger, you can increase alpha by moving this p star line to the left. How is that going to impact type 2 error? It's going to get smaller. Right? So you can see that as long as these curves stay the way they are, moving the p star line, we can either reduce alpha by going this way, but that increases beta, or you can increase alpha to reduce beta. And we'll get a little bit more into what else that means in a little bit. But I want to incorporate power into this. We said that power was the probability of correctly rejecting a false null hypothesis. The purple curve is a false null hypothesis, and all the area to the right is rejecting it correctly. So, where is the power in this diagram? It's the rest of the area under this purple curve. So if power is correctly rejecting a false null hypothesis, that is all the rest of the area under the purple curve. And so now we're really starting to see why power plus beta equals 1. Because together, they are all the area under this curve. We can also see the relationship now between alpha, beta, and power. If we move this line to the right, alpha gets smaller, beta gets bigger, power gets smaller. If we move P star to the left, alpha gets bigger, and power gets bigger, but beta gets smaller. So now we know power is rejecting the null when it's false, and that is the black area under the purple curve, and this shows that beta plus power equals 1. And we now see the relationship between those three quantities. A common question that I get at this point, other than what the heck's going on, is what about this area? What about all the other area when the null is true that represents when we fail to reject the null hypothesis? Well, I mean, if the null is true and you fail to reject, you've made the right choice, but that's not really what we care about. We care about making the right choice when the null is false. So this is good and everything, but we really don't call it anything. It's definitely the least important area of the 4. So I don't know, maybe it's just like, maybe just a winky face with a check mark. Like, you did a good job, you didn't make a mistake, but it's not really interesting, we don't really care. Right? So, I hope that this diagram has shown you a little bit more clearly the relationship between type 1 error, type 2 error, and power. And it really, a lot of it comes down to where this line is. And this line is usually determined based on the value you set for alpha at the beginning of the test. If you want alpha to be 0.05, you're putting this line here. If you want alpha to be 0.01, you're putting the line further to the right. And alpha of 0.1, you're putting it further to the left. That will also affect beta and power. Okay. Now, there is one last group of ideas that I want to glean from this, and that is how to reduce error or increase power. What are all the ways that we can, say, reduce the probability of type 1 error? Right? Because for a given hypothesis test, you can interpret what type 1 error means and say that that's a real problem and you want to reduce the probability of making that error as much as possible. What are the ways that you could do that? There are two main ways to reduce the probability of type 1 error for a hypothesis test. Probably the most straightforward is just choosing a smaller value for alpha, the significance level, when you start your test. Type 1 error is really the error that we have control over on our test. If we set alpha to be smaller, 0.01 instead of 0.05 for instance, that's going to move that P star value to the right. A consequence of that is it's going to increase your probability of type 2 error, beta, and it will also reduce the power of your test. The further you move that P star to the right, the smaller you make your type 1 error, you are reducing power, which is the probability that you correctly reject the null. So there is that trade-off there. There is another way to reduce alpha without moving this line at all. And we talked about it before. What was like the magic answer to how to reduce both alpha and beta at the same time. Increasing sample size. By increasing the sample size, how is that going to reduce type 1 error? How is it going to change what we see in this diagram? We're saying that increasing the sample size will reduce this area without moving this line. How is that possible? Remember, each of these two curves represent the sampling distribution of p hat. The sampling distribution of p hat has a mean and a standard has a standard deviation. Okay, the sample size affects the standard deviation. If you increase the sample size, that standard deviation is going to go down. That's actually going to change the shape of this curve and this one. A smaller standard deviation means more of the area is concentrated towards the middle of the curve. These tails are going to have less area in them. So without moving this line, if we increase the sample size, that is going to squish this curve with more of the area towards the middle, and this area will become smaller without moving this at all. And the interesting thing is, increasing the sample size doesn't just squish this curve toward the middle, it does the same for this one. So you can see how also squishing this curve with more area towards the middle is going to reduce the area in the type 2 error as well. So that is how increasing sample size reduces both types of error at the same time. So those are the two main ways that you can reduce type 1 error. Either just choose to have a smaller alpha at the beginning of the test, or increase your sample size. Now let's talk about the ways we can reduce type 2 error. There's actually 3 different ways you can do that. One of them, well, if we can choose to lower alpha at the beginning of the test by moving this to the right, and that increases type 2 error. What should we do to alpha if we want to reduce type 2 error? We should increase alpha. By being okay with a higher alpha, that's moving this line to the left, and that is going to reduce type 2 error. So simply by moving this line to the left, we are increasing alpha, that will decrease beta. Another way to reduce type 2 error, what we said here, increasing the sample size will squish this curve so that more of the area is to the middle. It will essentially make it taller in the middle and flatter in the tails. It's kind of hard for me to show that on the board. If we're back in class anytime soon, I will make sure to use an applet that will help you see that a little more if I can find one. But that is the effect of increasing sample size. That will also reduce type 2 error. I mentioned that there was a third way to decrease type 2 error. And that's really cool. We want as many ways as possible, right? We want to minimize the likelihood of making that mistake. Now, this has to do with where this curve is, specifically where the middle of it is. We assumed when we made these curves that there was a specific distance between our hypothesized value of the parameter and the actual value. But what happens if P is even further away than P naught? What if this curve was centered over here instead of here? What if this curve just kind of moved this way? Well, the line, this dotted line, P star, would stay where it is, but everything would move this way. That would reduce type 2 error. What do we call the distance between the parameter and the hypothesized value? The effect size. So the larger the effect size is, the smaller of a chance that you're going to make a type 2 error. Why doesn't that affect alpha? because effect size will only move this curve. This curve represents P being P naught. That's going to be the same no matter what. The only curve that will move based on what the effect size is the purple one. So we've talked about how to reduce both types of error, but we also want the power of the test to be as high as possible. So it would also be useful to know how can we increase the power of the test. But the thing is, we already know all the things that can increase the power of the test. It's the same as all the things that reduce the probability of type 1 error. Right? These things have to add up to 1. So if you want to increase this, you got to decrease this. And we already know all the ways to decrease beta. So all the things that reduce the probability of type 2 error will also increase power. So we built this entire example on an alternative hypothesis that P was greater than whatever P naught was. What if this were a less than sign? What about this would change? The only thing that would be different is that instead of being over here, the purple curve, where HO is false, would be on this side. Okay. All of the things that reduce the error and increase power would be the same. Some of the directions where I say move right or move left would be the opposite, but in general, you would still reduce type 1 error by lowering alpha or increasing sample size, and so on and so forth. If you had a two-sided test where P is not equal to P naught, rest assured, all of these things would remain true. What that looks like in terms of the diagram, I'm not going to get into that because it's a little more complicated. If you really, really want to know, shoot me an email or ask me in class, and I will rack my brain to try and figure out what that looks like. But I'm not going to worry about that right now. Just know that if you want to reduce an error type or increase power, these are the things you need to do. Either specify a lower or higher level of alpha. You can always increase the sample size. And in terms of type 2 error or power, you can mess with the effect size. So that is all the material for chapter 20 in the textbooks. So you should have a chapter 20 homework assignment due fairly soon. Check Canvas for that due date. You will also have one more video before the next progress check is due and the next quiz will be. So make sure to look on Canvas for when all those things are coming up. But hopefully this helped you put a lot of the stuff together that we've been talking about. Type 1 error, type 2 error, power. I've made it as clear as I think I can. So hopefully that helps. Hopefully you took good notes, and we will see you in the next video. Have a good one.